Hello and welcome again. In this next part, we'll look at the derivatives of three inverse trig functions: inverse sine, inverse cosine, and inverse tangent. The inverse cosecant, inverse secant, and inverse cotangent I'll give you. Those are palm tree derivatives. So I don't really have too many mnemonics here to give you. I mean, you just kind of have to take that first one. The derivative of inverse sine x is 1 over the square root of 1 minus x squared. Not too many mnemonics. Again, we'll go over the proof of this, and so the proof can help see where the square root is coming from, why there's a 1 minus x squared. But for now, as long as you got the derivative of inverse sine of x, that can help you then remember the derivative of inverse cosine x, because the inverse cosine x is the same thing but is negative. And we mentioned in the last part that the derivative of the trig functions that start with a c are negative, and it turns out to be true for inverse cosine as well. So that mnemonic holds up here. And then for inverse tangent, you don't have a radical on the bottom, but you do have a plus instead of a minus. And one way to remember that is that the t in tangent, in inverse tangent, looks like a plus. So t kind of looks like a plus, depending on how you write it. All right, so just a couple of mnemonics. They're not terribly good, but there's going to be some like rote memory for this, but hopefully that helps out. So with those in mind, let's turn to example 5. All right, so we're looking in example 5 at the derivative of negative 3 inverse sine x plus 2/3 inverse tangent x. And here the function is being called f of x instead of y. So we'll go ahead and use our prime notation, f prime of x. And again, we're going to take for granted the constant multiple rule and the sum rule that says that the derivative can distribute across pluses and constant coefficients can be pulled out of the derivative. So the derivative works its way into the inverse sine and the inverse tangent. So then we have negative 3 times the derivative of inverse sine, which is 1 over the square root of 1 minus x squared, plus 2/3, constant multiples always hang around, times the derivative of inverse tangent, which is 1 over 1 plus x squared. And then clean up a little bit. Oops, I guess I'll write this as 1 plus x squared just to be consistent. 1 plus x squared. There we go. And that's it. Well, video is only 3 minutes and 22 seconds here, so let's go ahead and just continue on. If I can switch over to derivatives of exponentials and logarithms. Now the derivative of e to the x is the best derivative of all because it's e to the x. It's the only function whose derivative is itself, so that makes it unique. And it kind of shows why that base e, that strange 2.71828 number, is, as it says, exceptionally excellent. It's because it makes the exponential function with such a base that the derivative of that exponential function is itself. The rate at which that exponential function is growing is equal to the y value at that point. Now, if you have the derivative of a different base exponential, so base a, where a could be anything like 2 or a half or whatever, then what you get is the same exponential but modified by this little ln of a. So there's a little times ln of a attached to the end of this derivative. Again, we'll prove both of these in a future packet. So the derivative of the natural log of x, remember that the natural log just means log base e of x, is 1 over x. So that one has a nice clean derivative and kind of makes a connection between this this function, this kind of ln x function, which is hard to get a handle on, and 1 over x, which is a rational function. It seems a little bit strange that there's a connection between those two, but this derivative makes that connection. Then if you have a different base log, like the derivative of log base a of x, where a could be anything, like again 2 or 3 or a third, that's going to be also 1 over x, but again modified by an ln a. This time the ln a appears on the bottom. It's multiplied to the bottom. So just remember, with exponentials, the ln a appears on the right next to the exponential function, and then with logs, it appears on the bottom. One way you could maybe remember that is if you have log base a right here, that a is a little bit down below, so that can help you remember that the ln a is going to be down below. The x is greater than 0 just refers to the domain of these two log functions. Log functions can only take positive values as input. Okay, let's go ahead and try the example 6. So here we have y equals, so when we take the derivative, we're going to have dy dx. We could also write y prime. That's another way of writing it, but dy dx is nice because it tells you what you're taking the derivative with respect to. That'll become important later on. So again, the derivative will distribute across the pluses and minuses. The constant coefficients can come out of the derivatives. So really we just have to focus on what the derivative of ln x is, of e to the x, and then the log base 2 of x, and also 5 to the x. So here the derivative of ln x is going to be 1 over x. For the next term, you can separate out the half. One half is the coefficient that's in front of the e to the x here. If we wanted to write on the side, another way of writing this term is 1/2 e to the x. So the derivative of e to the x is e to the x. So nothing much to be done there. The derivative of e to the x is e to the x, and that's the only function whose derivative is itself. Then you have the derivative of 5 to the x, which is 5 to the x, but then times ln of the base, ln of 5 in this case, plus 1/2 times the derivative of log base 2 of x, which is going to be 1 over x, but modified by ln of the base. And then the only last thing to do is maybe clean things up a little bit. We can write the first term as 4 over x. We can write the second term as e to the x over 2 if we want, minus 5 to the x ln 5. Nothing to really simplify there. I'll write this a little bit better. And then we have plus 1 over 2x ln 5. So that's the derivatives of exponentials and logarithms. Thanks for watching, and see you in the next part.